Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss some problems on Norton's theorem. In the previous video lecture, we carried out some examples on Thevenin's theorem, and we know that Thevenin's theorem and Norton theorems are dual to each other. So, if we understand the working of one theorem, we can easily understand the working of another theorem. The procedure to determine the Norton equivalent is by and large same as determining the Thevenin equivalent. So, just we do some problems and try to understand the working of Norton's theorem. So, here is a problem: find the Norton equivalent across AB terminals, and this question has been asked in AK2 2021-22, and the problem is like this. It is like this. Say this is I0 and find current I0. So, this is your 20 ohm, this is your J15 ohm, this is your 10 ohm, and this is your J4 ohm, minus J2 ohm, this is 5 ohm, and this is a voltage source of magnitude 40 angle 19 volt. So, this is the given circuit, and you are required to find the Norton equivalent across this AB terminal and find the current through I0. So, what you have to do? You have to draw this circuit. We have to draw this circuit. This is your RN, and this is, we say, the IN, or this is basically this is ISC, short circuit current across AB terminals, and then we place this resistance 20 ohm, J15 ohm, and we can find the I0. So, this is called Norton equivalent. It is dual to the Thevenin equivalent. So, in the Thevenin equivalent circuit, we have a open circuit voltage in series with an equivalent impedance, and here we have a short circuit current in parallel with an equivalent impedance or admittance, we can say. Procedure is same. If the network containing only independent sources, just replace the all energy sources by their internal impedance and try to find the equivalent impedance across the AB terminals. If the network containing both independent and dependent sources, so to find the RN, there are two methods. One is to take the ratio of open circuit voltage to the short circuit current, or apply a pseudo voltage source VDC across the AB terminals and replace all the independent energy sources by their internal impedances. The procedure is same. by and large Norton's theorems and Thevenin's theorem procedure is same. So, you have to find this circuit IN and RN. IN is nothing but it is the short circuit current across the AB terminals. So, what you have to do? You have to draw this circuit. You have to draw this circuit. This is your 5 ohm. This is your voltage source 40 angle 90 degree. Then this is your 3 ampere current source. Sorry, this is the given. This is 3 ampere current source. Then 8 ohm, then 10 ohm, 10 ohm, J4 ohm. This is your 8 ohm minus J2 ohm. This is your 3 ampere current. And you have to place, just remove this 20 plus J15 ohm impedance from the network and put as short circuit here, and this is your nothing but this is your IN. This short circuit current is IN. So, from this circuit you have to calculate IN. So, just try to visualize the current distribution. We can see that 3 ampere current is approaching towards this node and IN is leaving. So, current through this is 3 minus IN. Okay, 3 minus IN. So, current through the 5 ohm resistor is 3 minus IN, and you apply this outer loop. You take the outer loop, you can find the IN. So, apply Kirchhoff's voltage law in the outer loop. If it is better to just nomenclature, this is A, this is B, this C, and C is nothing but C is A. So, A apply loop A, B, C, A, because we have placed a short circuit here. So, this potential of this node is same as the potential of this node. So, C and A both are same, but just for the sake of clarity I have given the name here C. So, start from A to B. So, it is 40 angle 90 degree. Now, the current through this 5 ohm resistor is from C to B, okay, C to B, because it is 3 minus IN is from C to B. So, drop will be plus 5, 3 minus IN equal to 0. So, 40 angle 90 degree plus 15 minus 5 IN is equal to 0. So, IN is 40 angle 90 degree plus 15 upon 5. So, if we convert this in polar into rectangular, so it is coming 40 plus J0 plus 15 upon 5, so it is 11 ampere. Very simple. Initially the circuit looks very complicated, but if you go for the simplification, it is very simple circuit. So, only one equation, writing only one equation, we can get the IN. So, this is the IN is the 11 ampere. Now, this IN we have got. So, we got it, it is 11 ampere. Now, the next job is to find the Rn. So, we can write Rn. So, for Rn, because network is containing only independent sources, energy sources. So, we replace all the energy sources by their internal impedance. So, this is your 5 ohm, then here you have the voltage source, ideal voltage source, then ideal current source. Ideal current source has infinite impedance. So, it will be represented by infinite impedance. So, it looks like a open circuit. The ideal voltage source has zero resistance. So, ideal zero resistance will be represented by a zero resistance wire. So, it looks like a short circuit. And now put the value here, 5 ohm, this is your 8 ohm, this is minus J2 ohm, this is your 10 ohm, this is your J4 ohm. Look at, now we have to, this is your AB terminal. Okay. Now you have to look from this side, from the load terminals or AB terminals. So, if the current is flowing through this current coming here, so it has two paths, one is this one is this and one is this. This path has zero resistance, whereas this path has some impedance. We know that current follows minimum resistive path. The whole current will pass through this and no current will be through this, zero current through this. Okay. So, whole current is passing through. So, we can see that this B terminal is here, is B terminal, here is B terminal, here is B terminal. So, Rn which is equivalent impedance across AB terminals. So, Rn is 5 ohm. Straightway you can see that. So, whole current, because we have placed the short circuit across this, so zero current will flow through this. So, the impedance, so it will not take part into the equivalent impedance. Now, you can draw the circuit. So, Norton equivalent is, this is your IN, this is your RN, and this, now we just restore the impedance which has been removed to carry out the network Norton equivalent circuit. So, it is Z15 ohm, this is your 5 ohm and this is your 11 ohm, 11 ampere current. Okay. IN, this is IN, this is, we have to find I0. So, I0 using the current division. So, IN into impedance of this branch 5 plus 5 plus 20 plus J15 ohm using current division, rule. So, I0 is 11 into 5 divided by 25 plus J15 So, it is coming, if we calculate, it is coming 1.886 angle minus 30.96 ampere. So, this is the circuit way is very simple if you go for the analysis now. So, this numerical contains only independent sources. Now, we take another example having the both independent and dependent sources. And just we did it, we just we did it. Now, take another problem is find current, find IN and RN for the network shown below. So, it is also AKT examples in 2021-22. Okay. The problem is like this. This is your AB terminal, this is your voltage source 10 volt, this is your 5 ohm, this is the IX, this is the controlling, and this is a dependent source 2IX. So, it is a current controlled current source depending on the current of this branch. Okay, and you are required to find the Thevenin and Norton equivalent. So, you have to find this circuit. Replacing this circuit by this is your IN and this is your RN and this is AB. So, this circuit is replaced by this is called Norton equivalent. Okay. So, for now first calculate the IN. For IN, what you have to do, you have to place a short circuit across AB terminals. So, circuit will be like this is your 4 ohm resistor in, then here we place a short circuit. This is your IN, this is your 5 ohm, this is IX, this is twice IX plus minus 10 volt 4 ohm ampere. Okay. So apply this point, say this is A. Apply Kirchhoff's current law. Apply Kirchhoff's current law. Kirchhoff's current law at node A. At node A. So we can see that 2 Ix ampere and Ix ampere is approaching node A and In is leaving. So In is equal to Ix plus 2 Ix. So In is 3 Ix. Okay. It is better to write Ix dash because we have modified the circuit. So it is, say this is okay. So this is 3 Ix dash. Now look at here. We have placed a short circuit here. So this 10 volt voltage source is appearing. So in this circuit 10 volt voltage source is across 5 ohm also, because this is plus, so this is plus and this is minus, and Ix, for Ix point of view, this is plus, this is minus. So this 10 volt voltage source is polarity of this 10 volt voltage source is supporting the direction of Ix dash. So Ix dash is 10 by 5. So it is 2 ampere. Okay, and In is, so In is 3 Ix dash. So it is 3 into 2. So it is 6 ampere. So In is 6 ampere. Okay, now next job is to find the Rn, and we can see that the network is containing both independent and dependent sources. The procedure to find the Rn is either go for the VTS to the ISC, open circuit voltage, to the short circuit current ratio, or take a pseudo voltage source across this AV terminal, replace this independent energy source by the internal impedance, and try to find the ratio of VTC upon IDC. So we will just discuss both the procedures. Now for Rn. For Rn, so Rn is equal to VTH upon ISC. So this is your circuit, this is your 10 volt, 5 ohm, this is independent source, this is your VTH, this is your 2 Ix, and this is your 5 ohm, this is Ix, original circuit, and this is your 4 ohm. So this voltage, this is VTH. Now what is VTH? So we can see that Ix is approaching this, 2 Ix is approaching, so 2 Ix plus Ix equal to 0, so Ix is equal to 0. So in this case the current, the Ix is 0, so VTH is 10 volt, because Ix is 0, so no drop across this 5 ohm resistor. So this plus is, this 10 volt voltage source is appearing across this terminal, this is a AV. So, Rn is Vth upon Isc, which is Vth upon Rn. So, it is 10 by 6. So, it is 5 by 3, 1.666 ohm. So, this way we can calculate the Rn, or we can just approach the another method Vdc upon Idc. So, very simple, alternate. So, Rn is Vdc upon Idc. So, the circuit is like this. This is your 4 ohm. This 10 volt voltage source is replaced by its internal impedance. It is ideal in nature. So, its internal resistance is 0. Here we add a pseudo voltage source Vdc. This is your Vdc and this current is your Idc. This is your Ix, this is 2Ix, this is your 4 ohm. So, from this circuit you have to take the ratio of Vdc upon Idc. So, write the equations here. So, we can write Idc equal to plus 3 Ix is equal to 0. Okay. So, Idc is equal to minus 3 Ix. Okay. Now, take the another example. And this Ix, now look at this Ix is, this is like this. So, this is the short circuit across 4 ohm. So, it can be, the circuit is like this. This is 2 Ix, this is your Ix, this is your 5 ohm, and Vdc, the plus polarity is here, here is the plus, here is the minus. This is your Vdc, this is your Idc. So, we can see that for the current point of view, for Ix plus is here, for Vdc plus is here, minus here. So, basically Vdc equal to minus, or you can say the minus 5 Ix, or we can say the Ix is equal to Vdc upon 5. So, Idc is equal to minus Vdc upon 5. So, Vdc upon Idc 5 by 3, which is 1.66 ohm. So, this way we can carry out the examples on the Norton's theorem. So, this is the another approach to find the Rn. Take the ratio of Vdc upon Idc and replace all the independent energy sources by their internal impedance. So, this is all about your Norton's theorem. You do some more problems to just make your concept clear. So, we are stopping here. Thank you very much. Jai Hind.